Hey, this is Jet. So I did a dev talk at DevICT Presents a few days ago that we meant to live stream, and due to some last-minute technical difficulties, that did not happen, unfortunately. Turns out that YouTube now has this 24-hour waiting period for accounts I've never streamed before to go live, so I wasn't made aware of that prior to the event, so my 24-hour waiting period started about 10 minutes before the talk was supposed to start. So we weren't able to live stream it, but I know that a lot of people were actually looking forward to watching the stream or watching the video at some point. So I wanted to make sure I went back and did a video recording of it while it was still fresh and everybody still cared about it. So anyway, this is what that's going to be. I'm doing it live, so hopefully there will be not there won't be any post-production magic here. All the ums and ers and everything are going to be here. So. But it'll be hopefully as faithful to the actual talk that I gave as possible. So with that, I'm going to flip to my screen so you can stop having to look at me. Let me Google Hangouts freak out here. And we will pop over to the slides. Okay, so this is functional JavaScript with Ramda.js, or just Ramda, I think. This will hopefully serve as a gentle introduction to the functional approach of building software. I choose the term functional approach carefully because, functional programming itself is just one way of going about building software. It's not strictly superior or better than other paradigms like object-oriented programming or imperative programming. It's just a different way of doing it. I would say this talk is geared more toward an intermediate developer than a beginning developer. If you're an advanced developer with experience doing functional JavaScript with Ramda, then I don't know what you're going to learn here, but feel free to call me out if I say anything that's blatantly wrong. If there are beginning programmers listening, tuning in, don't feel like you should turn away, because this is one of those talks I think that will plant a lot of good ideas in your head and something you can refer back to later on in your career when you are faced with some problems that might be solved using this approach. So anyway. And of course, this is going to be a relatively code-heavy talk. I have slides, of course, but a lot of them link out to code snippets that I will explain and actually execute, so we can see the effects of running these things live. And they're all in JavaScript, of course. But the nice thing about this approach is that the techniques you learn here can be applied to many other languages. So just a little context as to who I am. Again, I'm Chet Durham. I'm a mobile web developer at High Touch Technologies here in Wichita, Kansas. Mobile web developers in quotes because that's just my title from HR. What I really do is cross-platform mobile apps with React Native. If you're not familiar with React Native, it's a cool, hot, sexy new way to write mobile apps in JavaScript that target both iOS and Android. It's pretty cool tech. This job was actually my first real project doing any sort of JavaScript at scale, and I kind of had freedom early on in the project because it was a greenfield project, to explore different avenues and different ways of doing things. I was learning everything as I went because I had never done React or anything like that before. So as I was learning this, I hit across this idea of functional programming and kind of dove deep in and learned some cool things and felt compelled to share that knowledge, because I think this knowledge can, even if you don't adopt functional programming as like the one true way, or anything like that, these principles I think can help anybody write better, cleaner, more maintainable code. So anyway, that's why I'm here. So before we get too deep into anything, I feel compelled first to define what functional programming is, at least at a really high level. I'll hit some bullet points here in a second, and you just kind of have to take my word for what exactly I'm describing here. I'll dive deeper into each one of these little topics as the talk unfolds. But functional programming, if you paid attention to any of the hype or anything like that, regarding just things in the JavaScript ecosystem in general, functional programming is pretty hot right now. It's an idea that's getting a lot of popularity in its current form. But it's important to note that functional programming itself is not a new thing. Functional programming has its roots really at the almost near the beginning of computer science. Alonzo Church did work with the so-called lambda calculus, which sounds difficult because it has that crazy word calculus in it. But really what it just is a formal mathematical framework for defining computer programs in terms of pure functions. It's actually a really elegant thing, and it's got just a few simple rules that have really wide-ranging implications. I'm not obviously going to dive really deeply into that because it's the rabbit hole on that one goes really deep. But it inspired languages early on like Lisp and Scheme that were functional in nature compared to earlier programming languages that predated C that were not functional in nature due to the limitations of the hardware at the time. But even if you look at pure functional languages these days that are seen as sort of darlings in the ecosystem, languages like Haskell, for example, is Haskell actually in its first form predates Java by 3 or 4 years. I think Haskell came out in 1990 and Java came out in 1994 or 95. So even though Haskell's getting a lot more mainstream attention these days, that's actually predates Java. So anyway, what functional programming is at a really high level is a programming paradigm. Its key constraint says that we take functions as values. Again, I'll describe what all of these mean in more detail later, but I'm just going to hit the high level right now and we'll go deeper later. The next thing functional programming describes is that it's a declarative paradigm. It uses pure functions without sharing state between said functions, without mutating data passed to those functions, and without generating side effects from those functions. So really, at its core, it's a relatively simple idea, but it's one of those things that if you really take these tenets to heart, you have to sort of work outside of your normal imperative box to actually build software in the functional, real valuable software, that is to say, in the functional paradigm. Why we would consider doing functional programming is also something that begs to be answered, because we've been doing Java and C and C# and all those more traditional paradigms for a long time. So why, and it seems to be working. A lot of people make a lot of money doing this stuff. So why bother with functional programming? Well, the idea is, we'll just do more high level points here, and I'll talk deeper into them later. But the idea is that functional code has a lot of advantages over more traditional imperative code. Functional code becomes more predictable. That is to say, it's easier to look at a piece of functional code and just immediately understand what it does. By that nature, it becomes safer as well, because you don't have to. You see that functional piece of code, and then you don't have to. You can be secure in knowing that it only modifies or only interacts with the things that it's says it is. It's not going to go do some side effect in a database or write a file or make an HTTP request, anything like that. Functional code becomes more modular. That is to say, it's easier to reuse functional code in a lot of cases. By their very nature, functional code is more testable, and in a lot of cases, you can actually write less verbose code in functional programming. Finally, before we get deeper into anything else, why functional programming in JavaScript? I mean, JavaScript traditionally is thought of as a more imperative or object-oriented paradigm. It has classes, it has inheritance, it has for loops, while loops, and things like that you traditionally associate with imperative languages. Well, the JavaScript actually has a lot of support actually for doing functional programming in the quote-unquote correct way, with this idea of first-class functions. Really, even if you've just started scratching the surface with JavaScript, you probably run across the callback almost immediately, even like just introducing yourself to jQuery, for example. You need callbacks in JavaScript to do anything interesting due to its single-threaded nature. So, most of us are already, even if we don't understand it or realize it, we are familiar with the idea of passing functions around as values in JavaScript. So given that support for first-class functions at the language level, we should aim to do functional programming in JavaScript because we can. I mean, that's kind of a weak answer, but really there's more to it than that, obviously. There's a lot of interest in functional programming from the wider ecosystem in JavaScript. If you look at really popular libraries like React, Redux, Ramda, Lodash, etc., these are all bringing functional programming to a wider audience than it's ever than it's ever experienced before. So, and it's disseminating a lot of those ideas that are coming from functional programming and applying them in a way that is forcing us to think differently. So we might as well kind of follow that rabbit hole and see where the trail ends and see if we can learn anything from it ourselves. At least that's my take on it. So anyway, before we do any descriptions, before we actually dive into functional programming, let's review do a quick review over some ES6 features that are bear repeating, just so that we are kind of on the same page in terms of our grammar and vocabulary and stuff. So the first two things I want to cover are const and let, if you're not familiar. Const and let are given to us by ES6 to help us make our intentions more clear when we're defining variables. In JavaScript, classically, the way you would define a variable is with var, and then you give the variable a name and then assign it a value. The issue with this, the reason that const and let have become a thing, is that there's a number of issues that var has related to scope. I'm not going to go too deep into that. I think it's a little outside the scope of our talk, no pun intended. But the biggest thing is that var provides no safety in terms of the value that you declare being reassigned at some other time. So in this example here, we take a var, assign it the value of 42, and then immediately assign it a new value of 1337. When we call it, like here, I scroll down to the output and we see that we get the second value rather than the first value. And again, this is because var doesn't give us any safety in terms of our declaration. You're free to change it however you want. So the idea is let and const let us be more clear to the interpreter whether we want our variables to change or not. There are some scoping improvements that come along with using let and var as well, let and const as well, that are again out of the scope. But if you look at what let does, let lets you say basically, I'm declaring this variable and I might change it later. And this is essentially the same use case we had used var for in the previous example that I just deleted, where we can declare bar with the let keyword, give it a value of 18, and then give it a new value, in this case 21. And then when we execute it, we see we get the new value 21, and JavaScript says, okay, that's cool. You said you were going to change it, so you're allowed. This might look that it's just the same thing as var, but it has a few other technical improvements over var related to its scope. So really, in the real world, it turns out that there's really not a good reason anymore to continue using var. In a lot of cases, you should be able to just do a find and replace to change var to let. If you can't do that for some reason, then there might be a deeper systemic problem in your code. Anyhow, const is the other new keyword for declaring variables we have now, where it lets you say, I'm declaring this variable and I'm not going to change it. In fact, JavaScript, I want you to yell at me if I try to assign a new value to this variable. So in this case, we give Baz the initial value of 88. We try to assign it the value of 35, and then immediately JavaScript throws this error saying that you can't do that. You said you were going to make it const. So anyway, that's let and const. Now there is one little caveat with const, is that it is possible to actually mutate the value that you assign to it. In this case, we assign the const bang a value of an object, and then when we echo it out, we see we have the object we initialized it with. But there's nothing keeping us from using this JavaScript syntax to add a property called C with a value of 3 to that object, so that when we echo it out again, we actually get a mutated version of what we initialized the const with. So I feel like that was an important thing to point out. If you've never seen let or const before, you might think that you can just assign anything to a const and it can never change. And it turns out that unfortunately that's not the case, just because of the way JavaScript works. So we will address how we can get around that in future. The next thing, or the last thing that I want to talk about with ES6 is arrow functions. Arrow functions give us a way to write out functions as or in a more concise and compact way. The classical way, again, of declaring a function in JavaScript is to use the function keyword, use the sum, and then give it a name, declare its parameters, and then provide some implementation for that function. In this case, we just return the sum of the two values passed in, or if they're strings, a string concatenation of those two things. So in this case, we get, when we call sum pair like this, we get the value 8 as we expect. Now, in functional programming, we're going to be writing a lot of functions. So if there's any way we can cut out some of this boilerplate, like this big old function keyword here, we should aim to do that. And arrow functions give us a way to do that. So we're going to just define another sum pair function, and this time we're going to use an arrow function to define it. So I'm actually using const here to say that I'm going to make a value called sum pair. I'm going to assign to that value actually this function. This function you could have done this with the function keyword too, but the arrow function syntax gives us a more concise and compact way of doing that. And the way an arrow function works is that you have this what they call the that arrow operator here. To the left, you have your input parameters, and then to the right, you have your function body or your output. In this case, we have the same function body and parameters we did before, so that when we call sum pair, we actually have the same behavior. In this case, we can actually do a little bit better because arrow functions also allow you to omit the return statement and the curly braces if you have a single line to the right side of the that arrow. In this case, it's an implicit return that you're returning the sum of x and y from this particular function. So in this case, again, we could just call sum pair 3 and 5 and get 8 as we expect. So that's arrow functions. Now that we know that, we can start to talk about functional software construction. That is to say, how do we actually build software with functional programming? There's one important concept that is the biggest driving force behind how we write clean code and how we write maintainable code. And that concept is abstraction. Programming languages themselves are actually abstractions. We're told, as we're told to keep our code dry and to not repeat ourselves. Programming languages essentially, the way we do that is through abstraction, where we write some behavior that we can reuse by passing in different parameters. Programming language. Again, I said programming languages themselves are abstractions as well, because computers don't really speak JavaScript or C. They don't speak any of those languages yet. They speak ones and zeros. So to get away from the programmers having to write ones and zeros, which was just intractable, of course. There was languages built on top of that called assembler language, and then there are languages on top of that, C, and then you can just keep building higher level languages, and all they are is just abstractions over how the computer actually computes things. So anyway, abstractions are a really important concept in terms of building software. So if we are building our abstractions by building functions and things like that, we have to ask how we actually use our abstractions. That is to say, how can we build bigger abstractions from smaller abstractions? And the way we do that is composition. And there's a compositional view of software construction, which is what functional programming really ascribes. Is basically the idea of building small abstractions and then composing them together to build medium-sized abstractions, and then medium-sized to go to large, and so on and so forth. And eventually your program at the highest level becomes an abstraction itself that is a composition of large abstractions composed of smaller abstractions, and it just goes up to abstractions all the way down. Now, how we actually compose, that's where our programming paradigm comes into play. So for traditional imperative or object-oriented programming languages, the way we compose bits of functionality together, that is to say, our compositional primitive is a class. And in functional programming, our compositional primitive is a function. So we have two sort of competing but complementary ideas in terms of what's the smallest building block we have that we can build compositions out of. So let's look at class-based composition first. And the point that I really want to get across is that class-based composition has its limits. And what that's rooted in is classes themselves are a really heavy primitive for composition. If you look at what a class has, it has a name, it has potentially a child classes, it has parent classes, it might implement interfaces, be related to abstract classes, and so on and so forth. It's got fields, it's got methods, internal state, all this other stuff. And I mean, there's just a lot of stuff that goes into defining a class versus defining a function. For example, the arrow functions we defined in one of the last slides, that was 3 lines long. A class that's 3 lines long has no content because, you're just getting started defining the class at that point. So what this leads to really is because classes are such a heavy compositional primitive, it's not necessarily intuitive how you can build some reusable patterns out of these things. And I think actually at some point, it's actually impossible in object-oriented programming to build some abstractions to the point to where they're reusable. And what this leads to is this idea of a design pattern. And what a design pattern is just a blueprint for creating an abstraction. We can consider this challenge of modeling a duck in an object-oriented way. And this is basically based off of a design pattern from the Head First Design Patterns book. It's the first one you learn. It's called the strategy pattern. And the way that you would, the challenge with modeling a duck is that not all ducks can quack and not all ducks can fly. So the idea is that you want to have whenever as you're making concrete classes, I guess, of ducks, you want to be able to give, for example, a model duck. You don't want to be able to give the model duck the ability to fly, but you want to give real ducks the ability to fly. So the way that's actually implemented in an object-oriented way looks something like this. I'm not going to actually unpack this. I don't know that it's necessarily important or useful to do so. But I mean, just consider that each one of those little yellow squares is in itself a class or an interface or something like that. And then all the arrows are sort of the implicit relationships between these classes and interfaces. And I mean, you can see there's just like a lot of stuff to keep in your mind regarding, this relatively simple task of modeling a duck in an object-oriented way. And this is actually, again, a really simple example. So the idea with function-based composition is that it's more expressive. And that's because it's a much lower level primitive. And a function on its own really is a better representation of what we try to capture an example with the idea of a behavior. So actually, I have this example here of a little snippet where I actually implemented the duck modeling challenge in a more functional way. And this is a kind of a simple, naive example, but it just kind of demonstrates the expressive power of being able to pass functions as values and using them as your compositional primitive. So in this case, we have a function called makeDuck, and it takes in, like the type of duck, some sort of descriptor. And then these two are functions that we're passing in. And if we look at the implementation, it's just returning an object that gives us our type. Then we expose two more functions on that object that basically just call the quack and fly behavior that we passed in when we construct this duck. So in this example, we have an arbitrary quack behavior and an arbitrary fly behavior. When we construct a redhead duck by calling the makeDuck function and giving it these behaviors, we can call the fly method on the duck, or it's a function. We can call the fly function on the redhead duck instance, and we see that it says I'm flying because that's the behavior we gave it. And so this is a simple example of how you can use functions to better express and create simpler and easier to understand abstractions than object-oriented programming generally gives you. And that's really the key, is that functional abstractions you build in functional programming, you have the mechanisms to build higher level abstractions. And this mechanism basically is what gives functional programming the increased modularity. We can build higher level abstractions that we can actually reuse rather than just having to reuse a pattern or a blueprint. And then this is also what helps us decrease the verbosity of our programs. Now, before I go farther, I've just kind of spent a few minutes kind of trash talking object-oriented programming a little bit. So I want to make it again really clear that I don't think functional programming is a strictly superior paradigm to object-oriented programming. They certainly both do, object-oriented programming obviously was designed and adopted for a reason. And, it's really good at modeling a lot of things that occur in the real world. It's just, it's not a silver bullet, and nor is functional programming. There are some things that are easier in OOP than there is in functional programming. So again, I'm not going to dive too deep into what's different there, but I just wanted to make that clear, that I'm not like, oh, Java sucks, whatever, that was my background. I come from a background of C# and Java and that kind of stuff. So and I think there's still obviously a lot of value to be working in those languages. So again, functional programming is not better than object-oriented programming. Now that we're 25 minutes into the talk, basically, I can start to introduce the Ramda library before I start actually diving into functional programming and learning some of these principles, because we're going to use Ramda to help us with that. So Ramda will look familiar to you if you've used libraries like Lodash or underscore. Ramda is partly a general purpose tool belt, just has like a lot of useful utility functions for, doing uh, diving into objects, doing null safe things, and so on and so forth. But really, it's also partly a critical piece of that is to say, it provides a lot of critical infrastructure for doing functional programming well in JavaScript. Not to say that you need Ramda to do functional programming. You just if you're going to be if you take that approach, you're going to be reinventing and rewriting a lot of stuff that has already been written. And anytime you do something like that, you're opening yourself up to your implementation having bugs and the time it takes to maintain that. It's just a lot of times it's better to just take on the dependency and let somebody else worry about testing that code. So anyway, um, what sets Ramda apart from those libraries are a few things. The first thing is its convention of how it accepts its parameters. It takes this convention of accepting its parameters in a data last fashion. So here's an example where we have an insert function that takes basically what insert does. This is an example of a Ramda function, by the way. R is the R binding is the global Ramda variable, and then of course it exposes all the functions on top of that. So what insert does is it takes an index, a thing, and a list, and says, with this list, I want to put the thing at the index I say. So in this particular instance, we have the index is the first parameter, which is 2. The thing that we're putting at that index is the second, and then the list itself that we're transforming is the last parameter. So you see in the output here, we have the expected result. We're saying put x in the second index. So we have 1, 2, x, 3, 4. What makes this different is the order of the parameters might seem unexpected to you if you're coming from like more of a Lodash type of a background. A lot of it seems more intuitive at first to pass the data first and then your transformative arguments. There's a good reason why Ramda does it this way, and we'll get to that hopefully at the very end of the talk, why it's like that. And then I'll do one more example here. This is the append function from Ramda, and it's a relatively simple operation as well. It just takes a list, it takes a thing, and says, hey, put this thing at the end of the list. So we have the thing is tests, and the list is write and more. So our output becomes write more tests because we're putting it at the end. So again, just an example of how Ramda functions take their data typically as the last argument. Okay, we'll skip the next one, the last one. Now, Ramda also has this interesting property of giving us a flexible ways of calling into it. So we'll just look at this insert example again. So the insert function takes 3 parameters. It takes okay, so we know what the parameters are. So interestingly, we can actually have a choice in terms of how we want to pass those parameters. We can pass those parameters like this, as you would typically pass parameters to a function, or we could do something like this, where we wrap each parameter up into its own little parentheses, like that, and we get the same output. We're just passing each input parameter independently. And we can also group maybe 2 of the parameters together and then call the other one later on, or vice versa. We can take out thanks REPL and then take that there. So anyway, like this, there's a name for what being able to call functions in this way is. We'll get to it a little later. But I just kind of wanted to show you this is another thing that sets Ramda apart. And actually, one of the more interesting things is that we can actually, we don't have to pass all the parameters at once. We can in this case, provide 2 parameters, however we want, like this. And then, it doesn't try to run the insert function with a missing parameter and then like break because we forgot something. It just in this case, it's returning a function. We'll talk about why we do that later, but when you consider that what I'm selecting here returns a function, doing this parenthesis here at the end of that is actually calling the function that comes out of that. So now we just pass in the missing input as input to the function that comes out of the first thing, and then Ramda then fully applies the function as we expect. So we'll dig more into how that's useful and why Ramda does that in a little bit. Okay. All right. So we have functional. Okay. So now that we've introduced the Ramda library, we've kind of justified what functional programming is and why we do it. Now we can really start diving into what functional programming is. Okay. The first thing, this is the underpinnings of functional programming entirely. Functions are values. So we've actually already seen this already. I'll pull up this example for posterity's sake. But when we say functions are values, that means that we can assign a function to a variable and then pass it around just as if it were an integer or a number or a string or something like that. So, and like I said, we've already seen this. This is a duck example again, where this function, to starters, we have this variable called make duck, and we're assigning it the value of a function, and then itself, it accepts functions as input and then does something with those functions. And this is a really simple example where it's just kind of giving you a facade over calling those functions, but still. And then we have more variables that are functions here. So anyway, that's sort of like the most basic underpinning of functional programming is that functions are values. There are still a number of programming languages that don't support passing around functions as values. Java is probably the most noteworthy example that I can think of. They have what they would call anonymous or lambda functions now, but they're not really the same thing. But any language that lets you pass around functions as values, you can theoretically do functional programming in. Python, for example, you could do. Okay, so now we can dig into declarative versus imperative programming. So declarative programming is this. Declarative programming describes what is done. It describes what your program does, contrasted with imperative programming that describes how your program does what it does. So if that's not too clear what that means, it'll become clear through an example. So we're going to set up a little test case here, and then we're going to have an imperative implementation of this function, and then we'll make a declarative implementation, and then we'll see the difference. So here's the scenario. We have a list of percentage-based scores, like for a classroom setting, and then we're just going to assign, we're going to give a letter grade to each one of these scores. And so up here we have our grading function. It's a relatively naive, just what you would expect. There's no curves, no pluses, no minuses. It's just a naive implementation of a grading scale. Now, so here's our implementation for actually transforming this list of scores into a list of letter grades. So imperative programming, again, describes how you actually go about doing the thing. So in this case, the thing is grading these scores. So how we would do this is going to look familiar. I mean, you would just go through, you would make a new list that's going to hold the letter grades. This is what we do here. I'm calling it a let because we're going to modify it. And then we do a loop over our passed in scores here, where we are in our loop body, we're taking the value out and calling it score. And then inside of that loop body, all we're doing is pushing a new value to the array we initialized up here. And that value is defined by running the score that's in the list through the grade score function to get it to transform it into a string. So then once we've run through all of that, we'll have a list of strings instead of a list of numbers, and we just return the thing. And then, so actually, if I add a line to execute with our data, see what we get. We out of the output, we get what we expect. We get a list of strings, a list of letter grades, and that's what the imperative implementation of this thing looks like. Now, functional programming says that we can do this better because instead of saying that, oh, we're going to do this grading by looping, by making a new list and iterating and doing a loop over this thing, and then every step in the loop we're going to run this function on the value. We want to capture the idea of doing that same thing, but at a higher level. And functional programming takes, there's a word in functional programming that captures the essence of that idea, that is iterating over a collection and then transforming each value in that collection given some transforming function, and that's called a map. Or map, I suppose. And so this is a declarative implementation using map of the same logic that we wrote up here between lines 11 and 18. So we have declarative grade, takes in the same list of scores, and then it's calling the built-in ES5, I think, map function on that list, that array, and then in the function, we're saying that we're going to map over scores, and then we want to run this grade score function as our mapping function. So when we run this, we'll see that we get the same output that we got from the imperative implementation. It's just a much we're leveraging a higher level abstraction to capture this idea of iterating over a collection. And in that case, in this case, it's much more. It's a lot less verbose for starters, and then it's once you understand what map means, it's pretty easy to read this and say, oh, okay, so it's just taking scores and mapping them to numbers, via this grade score function. So that's sort of what what declarative and imperative look like in practice and compared against each other. I just closed my slides. Did not mean to do that. Loading deck. Okay, let's get this started back up. Okay, live streaming, gotta love it. Okay, the next thing we'll talk about are pure functions and referential transparency. These two things, they do have, I think, a technical difference in their meaning. But for the scope of this talk, at least, I'm going to pretend like they are basically the same thing. And until you are really care about the differences between them, you can just kind of assume that they both mean the same thing. Again, this is what gives us the predictability and safety in functional programming. And what a pure function is a function that returns some output that's based entirely on what you pass in as input. That is to say, they don't depend on some external state. A pure function is not going to go out and just read a file and pull in some data and do something with that. It's a pure function would instead expect to have that data passed into it when it's called, and then it does some transformation on it. So, and then pure functions should do one thing well. So we'll look at a few examples because there are three key considerations for implementing pure functions. The first key consideration is to not mutate data that you pass in. So here's an example. And when I say mutate, I mean change. So here's an example of a function called add username. It's going to just take in some arbitrary data, probably an object. We're going to add a username property to it, give it a value that happens to be my name, and then we'll return the thing. So, and this looks fine because we're returning the data that we pass in, but it's not immediately obvious. And if you've done this in JavaScript, but it's not immediately obvious. It's that because you're returning the data, it's not immediately obvious that this is actually going to mutate the data that's passed in. And so to prove it, I have a test case here where we call this function. We define some data. We're going to log it out to start with. We'll run the add username function on it and capture the updated output. And then we log that. And then we go back and log the original. And when we do that, let me clear the output here and run it again. When we do that, we see actually when we go back and log the original, it has the change from the function. And this is not what we want to do in functional programming. We want to, when this data gets passed into it, we don't want to have this function change it. We want, if there's a change to it, we want it to return a copy of what we passed into it with the changes made. So we can do that with Ramda. You can do that with ES6 too, with like the spread operator and stuff like that. But because this is Ramda talk, we're going to do it with Ramda. So, so I will find it's like here. This is probably my least well-prepared snippet. Okay, so now I have essentially an immutable implementation of the same logic here. Takes in a data object, and instead of assigning the property to the value in this way, we're going to leverage this Ramda function that's immutable in nature. And that's another thing I should have said earlier, is that all of Ramda's data transforming functions are immutable. That is to say, they return a copy of the data that you pass in with the changes described or declared by your function parameters. So in this example, this function is called assoc or assoc. I don't know. It's short for associate, I imagine. And what it lets you do is say, hey, I have this object and I want to give it a new property with this name and I want to give it this value. So in this case, we're saying I want to assign to data a property called username with the value my name, hard-coded. So now we have this my date. So now if I just replace the call here with the immutable call and then examine the output, we see the original output is what we anticipated and what we desired. We don't want to have the original data modified. So we've essentially, by making this immutable, we've made this now a pure function because it's not mutating the data that's passed in. Okay, the next key concept is pure functions do not have side effects. Now, what a side effect is, I probably should have had a slide for this, but a side effect is basically something that goes and does some effect on the outside world. In practice, side effects are generally I/O or input-output based things. Querying for some input from the user would be an example of a side effect, or going out to a database or a file, or making an HTTP request to get some data or send some data. Those would all be side effects. So if we look at this example here, we have a function called getSum that has a side effect. It has a console.log in there, and this is sending this output, or this parameter here, just sending it as a string to the console. And that's a side effect because it's doing some output to the screen. And when we have side effects on our functions, they become less modular because there's a lot of times where we might not want to do that side effect. And if you just look at this function right here and pretend that the getSum function is defined in a different module or a different file somewhere, it might not, and you just run the getSum function to do something. Supposing I was capturing the output here like I should, you wouldn't know that it does some sort of side effect until it's too late. In this case, it's an innocuous side effect, but it could be something like deleting stuff from a database or something like that. So, okay, so the idea is that pure functions should not have side effects. So we can very easily make this function a pure function by removing the console.log. We're going to move it to basically the farthest out point of our program we can. And then I'm going to, instead of just, I'm going to actually capture the output of getSum. And now when I log it out, I see that the sum is undefined because I did not return the sum of my getSum function. And in this case, and this implementation actually uses the sum function from Ramda to sum up our number list very easily. So now we have what we expect. The sum is 42. And so this idea of moving the side effects out of the functions and to the outer edges of the program captures the idea of, you hear sometimes in functional programming, of having a functional core, and wrapped around that having an imperative shell. Because what it really is that, a function without side effects or a program without side effects is a program that is not useful, because side effects are how you can get input into the data, into the program. It's how you get output out of the data. And if your program doesn't take any input or accept any output from the real world, then what is it doing? So so the idea with side effects is that you want to put them as far out on the edges of your program as you can, and that helps keep your functions and your logic, your actual program logic, as pure as possible. And then your side effects is very clear where those happen in that case. Okay, so one more thing on pure functions is the idea of not depending on global state. So I'll just explain what that means. We have a data object here. This is going to be our global state. We just define some users in there. We define some posts in there. And then we have this function at the bottom that says get post by ID. So it takes in an ID. And then we're going to use this Ramda function called path that basically lets us pass in a list of strings to basically describe how we dive into the object to get a value out. And then it takes the data too. So now when we say get post by 2, it's going to follow the path that's described by post and the ID that we pass in, and 2 in this case, to the data. So if we actually do that ourselves, we dive in starting at post, and then we go to 2, and this is our data that comes back. So this is what should come back from our function. And if we go down, we see that that's what we got. Now, the problem with this function is, again, it's not pure. It does not depend entirely on what's passed into it. We're only passing it the ID, but we're using the ID in the function, and we're using this global data object. So the idea is that we don't want to depend on the global object here. We actually want to have this function accept the data as an input parameter. So in that case, we would pass in, we can make this pure by just defining a variable to capture the data and doing it that way. I just gave it a different name to disambiguate. So now, of course, we're calling get post by ID, and we're not actually passing in the data. So data is our global state. We just pass it in, and then we get the same result. So this is the idea of having your functions not depend on global state. They should instead expect to have everything that they're operating on passed to them explicitly. So, and this helps reduce. This is what makes functions, pure functions, parallelizable. It's not really a concern for JavaScript so much as it is in FP in general. But passing in all of the input that a function needs helps make functions testable, and it helps eliminate entire classes of bugs, actually. Okay, now the next thing we'll talk about are immutable operations, and basically we already covered this, but we'll go through it again because I want to take the opportunity to show off my favorite Ramda function. So the idea again is not to mutate the data that you're given. So here's another example that demonstrates how we can leverage Ramda to write implementations that are immutable in nature. So in this example, we have a state object. Relatively simple. We have a function that's going to take in that state and return some new state. Maybe this is like a Redux type of example. So this function is called to next page. Its implementation is to take active page on that state and increment it, and then return the new state. And returning the state does what you'd expect. But when we call the increment operator like this, it's a mutating operation. So we have some console logs here where we're executing the thing, and we see when we go to log out the original state again for the second time after running it through this function, we see that the active page has gone from 3 to 4, and we wanted it to stay the same. So let's use Ramda to make this more pure, or let's leverage Ramda to make this a mutable function. It will make it pure, but it's more focused on immutability at this point. Okay, so here's the implementation. We have to next page, takes in state. Okay, so we're going to use this function called evolve to declare a modification of our state in terms of functions. And so what evolve lets you do is it lets you specify a transformation to an object in terms of functions applied to its values. So in this particular example, our state object has a value called active page. And the evolve object we're passing to it, or the evolution object, I guess, you pass in an object that has the same shape. And if there's a key or a property in the evolve object that it shares with the state object or the object you're transforming, it will execute whatever function in the evolve object you've described on that value. Okay, so in this example, I'll walk you through it. We have an active page function in our evolve, and what we do in this case is we're just saying which is short for increment. So we're just going to increment whatever is in the active page for this particular object. So passing in this state, it would just take the active page and go to 4. The difference from the last implementation is that it actually returns a copy of the state and not it does not actually modify the original state. And again, that's because Ramda does not modify its input. It's designed to be functional programming stuff. So here's what we see. We see active page in the original is 3. And when we log out the original again, after running the function, it is 3 is a 3. It stays 3. And then the modified version has the active page going to 4. And that's what we wanted. So, okay, that's immutable operations, just bear repeating. Okay, map, reduce, and filter are the big ones. That's what a lot of people talk about in functional programming. It's not all functional programming is, despite what some people would have you think. But here's what it is. Map, reduce, and filter are sort of the high-level ideas behind doing list iteration. It's a little bit more subtle than that in the technical functional programming world. When you start considering things, defining things like monads and that kind of stuff. But I don't understand that stuff well enough to teach it, and so I don't think that it's necessary for me to talk about it here. So anyway, as programmers, we deal with lists a lot, and for uh, imperative programming languages, it's actually difficult to write good abstractions over iteration. Some languages have implemented these things called generics that aim to help us write, reusable iteration functions. C# has an entire subset of its language called LINQ that lets you do kind of the same thing. But what they really are all is different flavors of these functional ideas of map, reduce, and filter. So we'll just kind of step by them one through one. I'll walk through some implementations. I'm not going to actually walk through the implementation of reduce because it's just kind of, it's a lot to explain, especially in the context of a talk. I didn't explain it the other night when I was doing the real talk because it's something that I think is better learned by example and by actually playing with it. And I don't know that I could just really do a good job of explaining it to make somebody understand it in the context of a talk. So anyhow, so we'll start with map. So again, what map is, we saw this earlier, but map is the idea of iterating over a list let's not say iterate, but it's the idea of taking every value in the list and transforming it to some other value. Some of the important things to note about map is that a map operation will retain the list's dimensionality. That is to say, if you map over a list with 5 elements, the output will be a list of 5 elements. A map is never going to make a 5-element list go to an 8-element list or something like that. So a map is defined very simply by the collection you're iterating over. In this case, here's our collection, and then the function that serves as your transform for the value. So this is the original implementation we had where we were using the built-in map function on an array to do the iteration, but we'll refactor this to use Ramda's idea of map. So Ramda has a map function, and so you got to remember it takes data last. So if our map operation is only defined by a function and its data, then it stands to reason that it would first take the function, which is grade score, and then the data. And if I spell this right, when I run it, I will get the expected result of just a list of letter grades. Okay, so that's map. Take the list and transform it by some function. Okay, now a filter basically is an operation that lets you specify some criteria to basically filter elements out of the list or to accept elements into a new list. There's 2 different ways you can think about it. Ramda has a filter function that serves as a what does it see? Less than 80. The Ramda filter function lets you describe a criteria to I think it's to reject. This whole Boolean logic thing, I have to. I usually have to write these functions twice. The first time I'll write it with the criteria function being backwards, so you have to forgive me on that. But what filter lets you do is let you shrink the dimensionality of a list. We're not doing transform on the list. We're going to have a list of numbers, still be a list of numbers in this case, but we're going to have a smaller list of numbers because we're saying in this particular example that I have shown here, I want to drop all of the scores that are less than 80. I want only A's and B's. So this is implemented by saying our filter. And then this is our filter function. In the context of functional programming in general, these types of functions that take in some value and return a Boolean are called predicates. Good thing to know. I probably should have it on a slide somewhere. Anyhow, we use the LT function, which is short for less than, from Ramda to do this. I could have done this with the less than operator in JavaScript. I could have actually rewritten this function a little bit more concisely, but that's one of the next topics, so I don't want to spoil it yet. So anyway, here's our filter function, here's our scores. When we run this thing, we will get a list of numbers that are out of that original set that are, or that original list, sorry, to be precise, that are less or more than 80, that are not less than 80. Anyway, Boolean logic, gotta love it. Okay, now a reduce is the most flexible, the more, I guess I should say, the most generic way of, how do I want to say it, the most generic list iteration abstraction that I think is commonly thought of, or in the common perception of functional programming. It lets you grow and shrink the size of a list. It lets you freely transform the values that you're operating on. You can even take a list of numbers and then output a string. You don't have to reduce into a list or something like that. So again, I'm not going to actually walk through the implementation here because I think it's a little heavy. But essentially what I can do with a reduce is have a function that combines the operations that we did before in the filter and the map. So in the map, we were just transforming the numbers to letter grades, and then in the filter we were dropping certain numbers if they were too low. So in this case, I'm dropping the dropping the numbers first, and then if they pass, then I apply the grade score, and then I'm taking a list of 7 numbers and converting them to a list of 4 strings with one function, basically. And here's the function, and then here's the calling of said function on the data. So anyway, if that sounds interesting to you, you should definitely kind of dig into reduce and see how it works, and then play with it a lot to really fully understand it. Okay. All right, now we're moving. Okay, oops. Okay, I'm just kind of figuring stuff all over the place here. All right, higher order functions are next. So I think there's 2 forms really of higher order functions, one of which we've already seen in the examples of map, filter, and reduce. So these are functions that accept functions and then do something with them. That's a form of a higher order function. So we've already seen a lot of that. But higher order functions can also be thought of as the idea of having a function that returns a function. So what that looks like in practice is something like this. If you remember back to our get post by ID implementation, where we had the data and post ID passed as just comma separated input parameters, we could instead implement it like this, where we have it takes in one parameter, it takes in data first, and then it returns this, which is returning another function that takes in the second parameter, and then finally we're applying the path to both post ID and data. So we can actually make this a little bit more concise with arrow functions and omit the curly braces on the return, and we would have something that looks like this. So we have this function is get post by ID. It takes in data, and then it returns this function that takes in post ID. This function, the other function, returns the actual calling of Ramda's path function. It's probably not immediately clear or obvious why this is useful. And to talk about that, we'll have to talk about currying functions. What a curried function is it allows us to what you would call partially apply a function. It basically allows you to call a function with only some of its parameters and then defer the final calculation until you pass in the last parameters at some later time. This is actually how we describe Ramda's library functions. Remember way earlier on in the talk when I talked about how Ramda functions were flexibly callable? That's because all of Ramda's functions are curried by default. They're actually a special form of curried where they can be called in the functional way with parentheses or with the comma separated typical way. And we'll look at some examples about how we can make our own curried functions. So this particular function is the 3D vector length function. You just sum the squares of x, y, and z and then square root the whole thing. So here's an example where I'm computing the length of 1, 2, and 3. Okay, so now let's write a curried implementation. So the disadvantage with this the particular function is that you have to pass in x, y, and z all at once. I can't pass in x and y and then pass in z later. So let's write an implementation where we can do that. And we curry functions by leveraging this idea of higher order functions, where we just take the input and separate them into individual functions, where we have this compute length function takes in an x and returns this function. This function takes in a y and returns this function. This function takes in z, and then now we're actually defining this curried function in terms of the original 3-parameter function. And we just actually do the math at this point. So we would call this function like this by passing in all the parameters, and we get the same value. So this doesn't really capture the idea of how curried functions are useful. So to do that, suppose that I had a situation where I wanted to fix x and y, and then have a compute function that only took in a z, and then would compute the length of a vector given z, given that I have my x and y defined. Suppose that that's something that I care about. I don't know, we can give it some name, whatever, give it a good name. I can say that this function is equivalent to this partial application of the compute length c function. So now, when I call this function, I actually get a function. And in this case, you can actually see that it takes in a z and then returns the application of the final function. So now if I passed in 1 and 2 before. So if I pass in the original z value we've been looking at this whole example, I actually get the value you've been seeing for the whole example. Okay, so the issue with currying this way is that, see how we had to call this function here to actually partially apply it? It's not very JavaScript idiomatic, right? We like to pass parameters to functions with commas, and like this extra parentheses stuff is just kind of, it feels a little gross. Like I feel like I need a shower or something. So we can actually, and like if you remember how Ramda's functions are curried, we can actually we should be able to pass in like the 1 and the 2 like this, right? And then call the last function, or call the final function with the last parameter like this. But we can't do it the way we've done it like this. It's just not flexible enough to do that. So we have to call this particular function sort of what I would call like a manually curried function. I don't really know a good technical word for it, like this. So the good news is that Ramda provides us a helper to generate a curried function in its sort of idea of curried functions that can accept parameters flexibly. So that function from Ramda has the name you'd expect, curry. In this case, we just pass in the original compute length function that's not curried to return a new function that is Ramda curried. We'll call it Ramda curried. How about that? Okay, so now I can call this function like this. I can pass in the 1 and the 2 together, and then pass in the 3 separately. So if I take off the 3, I get a function that takes in 3. Now in this case, this output here is a little bit less obvious because Ramda does a whole bunch of crazy stuff under the hood. I wouldn't really count on this output ever to be descriptive of anything personally. But now that returns a function, so I can just pass in the 3 as the last value. And of course, if I wanted to, I could just pass in all the parameters and then have it work. There's another interesting thing we can do with Ramda curried functions, is that we suppose that we had x and z, and we wanted to have a function that we would pass y to. Well, in this particular case, it's not clear how we would do that. Like over here, we would have to define like another curried variant of the function that took x and z and then took y at the end. But with the Ramda curried function, we can be a little more flexible. There's this r.__ primitive that is included in the library that actually serves as a placeholder in any Ramda curried function. So in this case, I'm saying I want to call compute length, partially apply compute length RC with the x and the z, and return a function that lets me pass in the missing parameter, y. So again, this returns a function. And then if I pass in the missing parameter 2, I get the expected value. So, okay. So that's currying. Again, probably not immediately useful or immediately clear why that's useful, but we'll get there really quickly when we look at pipe and compose. Okay, before we get to pipe and compose, though, I want to talk about point freestyle, because really to make pipe and compose useful and make sense, we need to leverage point freestyle. So point freestyle, or tacit programming as it is formally defined, is basically a way to make our code even more concise by removing redundant declarations. It's something that is not immediately obvious. It certainly wasn't immediately obvious to me when I first saw it. But you can basically just kind of like look for a pattern and then like apply this as like a trick, kind of yeah, like some math trick, that's based on a pattern until you really understand what it really means. So we'll look at an example, and then have a function, and then we'll convert it to a point-free syntax. So here's a consider this function where we have a get a. It takes in some data, and then we're going to use the prop function from Ramda to say, hey, I want to get the value for this property or this key given some data. So if I have my data object that has a capital A property, and I call get a on it, I will get the value at the capital A. Makes sense. Okay, so we can make this get a function a little bit more concise by converting it to a point-free syntax. So how we do that, first off, we have to leverage the idea that Ramda functions are curried. So instead of calling the function like this, we can instead call the function like this and not break anything. Okay, now here's the pattern. I will show this to you, and then I will step back, and then I will explain what I did. But essentially, this declaration of get a is equivalent to this declaration of get a. Okay, see, I got the same value, 1. If I change this, so we're still running the same get a, but we're running it's a much more concise way of defining get a. So let's step back through and explain what I did and why I did it and how I knew I could do it. First off, the pattern is this. If you have some input data, and the only thing your function body does is apply it as a parameter to the end of some other function, then that's your signal for saying, hey, I can make this point free by deleting these two. It's redundant to say this. Okay. Now, why is it redundant? So, okay, here it is. When by doing this, we're splitting up the prop function from fully applying it to partially applying it. Okay. So when we consider what this is, this our prop here is a function that takes in some data and then returns the fully calculated value. And so it turns out that what it takes in is just this thing here. So when I say this is equivalent, I mean that this R prop here is the same thing as a function that takes in data and applies it to the end. So we don't actually have to pass in the parameter. So anyway, that's point free. It can be a little bit disorienting when you first see it, especially because we're used to having functions really be explicit about what they take in. But this approach to doing point free syntax, once you get comfortable with it, will not only make your code easier to read and understand, it'll also hopefully make your code a little bit more flexible and kind of like lead you down the path of writing more maintainable and modular functions. So now everything that we've learned so far in terms of functional principles have led us to this point. Essentially, all that we've learned so far is basically telling us how we can write the best reusable modular functions that we possibly can. And now it's the time to consider how we can chain those little functions together to create higher level abstractions that we can themselves be reused throughout the rest of the application. And this is where the real power, at least to me, this is where the real power of the functional approach comes in, is that these operators, these pipe and compose ideas allow you to be really flexible in how you chain functions together. They don't have a lot of boilerplate. It's essentially like my ideal thought patterns sort of expressed in like real code without any extra cruft. So we can look at these examples. And so I just wanted to make it clear that pipe and compose to me are like the most important things that I've talked about so far, but we really did have to go through all of that other stuff to get to this point to where we can actually make it useful. Okay, so here's the first example. So we have a little test case here. What we're going to do is we have a string, or we have a comma separated string of letter pairs. What we want to do is have some logic that returns the string, that basically filters duplicates from these strings and then uppercases the strings as well. And they need to be returned in the same format, comma separated letter pairs. So let's examine how we can do this. So we'll leverage Ramda functions for each step of this. So the first thing we'll do is we'll go ahead and just uppercase the entire string. And we'll use a Ramda function called toUpper to do that for us. So it does what you'd expect. It takes in a single parameter and just returns the uppercase version of it. So instead of this little literal here, we will pass in our data, and we're off to a good start. We've got the letter pairs uppercase now. Okay, so now we need to consider how we're going to drop the duplicates out of this thing. So the best way that I know of to do it is to take this string and convert it to a list. And once we have it in a list, we can run it through an easy operation to deduplicate it. So we can use the Ramda function split. And what split does is it lets you define a splitting character and then a comma and then a string where that splitting character is contained, and it will just return a list where every element, and it just basically goes through the string and then makes an element by looking between the splitting characters. So of course we don't want to split the 1, 2, 3 literal. We want to split the output of our toUpper. Oh boy, now I've done it again. Now we have, instead of a comma separated string of uppercase letter pairs, we have a list of uppercase letter pairs. Now with this list, we can really easily deduplicate it by using Ramda's unique function, short for unique, I suppose, that lets you pass in a list or an array with duplicates, and it will just filter out the duplicates for you. So of course, this literal array is not useful to us. What we want to pass to it is what we've gathered so far. Okay, so now we're really getting somewhere where we have the uppercase letter pairs and they're all unique. So now the last thing to do is just put them back together in a comma separated string, effectively undoing the split operation. So easy to do with Ramda's join function. Just lets you pass in a list of things and a joining character, and then returns a string with all those things glommed together with the joining character. And of course, the 1, 2, 3, 4 literal is just an example. What we really care about is everything we've got this far. Okay, good. So that's the desired output. Now the last thing to do is to make this a pure function, because if you remember, my data in this case is like a global state, and this function to be modular, we want to be able to pass different forms of data to it. So we just need to make it a function. We'll call it like sanitize. And then we'll have it take data as an input parameter. And then we'll just operate on the data. And we run sanitize with my data. We get the desired output. Okay, so I mean that's good, right? And this is essentially how we chain together, larger abstractions, really in any language, in any imperative, be it imperative or functional. We just run a function and then pass that output to the next input, and so on and so forth. The issue is that this particular declaration here is not very readable, right? Like it's a declarative, but like to unpack it, like you have to know that you're starting from the inside out. You have to trace, you have to like line up the parentheses, and then it's just not very readable, right? It's not very predictable, I guess I would say. So pipe and compose give us a way to capture this idea in a much better way. So with that, I'll skip over to the next example because this has a lot of stuff pre-typed. So here's again our sanitizer function in our data, and we're running sanitizer to get the desired output. Okay, so how we typically do this in imperative languages, of course, because this is so hard to read, this would not pass anybody's code review. So what they would expect you to do would be to split it up like this, basically just splitting up the all of the different allocations. Okay, so or splitting up the calculations, not the allocations. So we first run the toUpper on the data and capture that result in an intermediate and like a temporary variable, right? And then we declare the split, in terms of that intermediate variable right there. Okay. And then so on and so forth, we capture that here and then pass that to unique here. We get the unique, and then of course these variable names wouldn't pass code review either, but it's enough for our example here. And then and in there, yeah. So there's our output. So then when we run this version of Sanitizer, we get the same thing. Supposing that I have it spelled right, but I had it spelled right. What have I done wrong? Oh, this guy up here. So that's how we would normally do it. Okay, so now here's the problem. This, you don't see this in functional programming because there's a pattern here that we can abstract. And so here's the pattern. We have a function that takes in some data, and then it does one step. And then it takes the value that we get out of that first step and then applies it to the next step as the last input parameter here. And then so on and so forth. The output here, or the output here becomes this guy's input, and the output here becomes this guy's input, and we return the final output. Okay, so we can abstract this out with functional programming. We can, the abstract concept that we can leverage here is called pipe. And so here's how it looks. We have this piped version of Sanitizer that takes in data, and then we say that it returns r.pipe. So we're passing in the data all the way at the end here. And this pipe is actually a reusable composition of these 4 functions. Okay, so we're leveraging point-free syntax in this declaration here. So here's how it reads. We have our pipe, it takes in data. Data first gets handled by toUpper. toUpper only accepts one input parameter. So it runs the toUpper on the passed in data. And then the output of toUpper gets passed as the last argument to this function. And now, so we're actually leveraging Ramda's curried ability to, Ramda's curried functions to partially apply split in this case, where we're saying this is a split on comma, basically. And then that function takes in the uppercase string. And then this gives us a list that's passed to unique. And unique is what duplicates it for us. And again, unique only takes one parameter. So the input parameter is implicit. Again, remember point-free syntax. Instead of writing it this way, we can write it this way and not lose any meaning. And then finally, we have this join with comma function that takes in the unique list here and puts it all together. So our Sanitizer P implementation has the same output as our original Sanitizer function did. And so actually, okay, we can actually make this whole pipe a little bit better too, because we can apply the point-free syntax pattern to it. See how we have data here? And then the only thing we do with it is apply it as the last parameter to this pipe function. That means we can make this whole thing point-free. And then, so now our Sanitizer pipeline looks like this. And this is very readable, right? Once you understand the idea of curried functions, point-free syntax, and partial application, it's really easy to understand what this function does. It runs toUpper, it does the split, it does the unique, it does the join. It's a really easy way to express this algorithm compared to either the original implementation that was really hard to unpack, or this one, which is easier to read, but has a lot of unnecessary boilerplate. Okay, so what pipe lets us do is so-called left-to-right function composition. Pipe is really, if you've done any Unix shell stuff, you know how piping functions together works. Same basic concept. Ramda's compose function is like pipe backwards. It lets you do right-to-left function composition. So we have the same pipeline here. We can again make it point-free because of our pattern knowledge. The only difference between this and Sanitizer P is that it's quote unquote right to left. In this case, it's bottom to top because it's easier to read that way. But this actually reads the same way as this guy does up here, where we have inside out, basically the same way. That's our inside, that's our out. I prefer pipe personally. It makes more sense to me. There are a few times where I would consider putting a compose together, but For the most part, pipe's where it's at for me. And to me, like, this is sort of like the ultimate expression of the power of functional programming, is that it lets us be a lot more explicit or implicit about, wait, which one is it? Explicit or implicit? It lets us basically be more implicit about all the unnecessary boilerplate that we need. Functional programming lets us be a lot more concise and less verbose and higher level abstractions and all that good stuff. Anyway, okay. So that's all I had to say about functional programming, at least all the principles of it. There are a few things I want to go over to basically address some of the criticisms of functional programming in JavaScript. I think they're valid. The first criticism you hear a lot is that functional programs are hard to read. And I mean, I guess I can kind of agree with this. If you've never seen Ramda before, and like all of your programming experiences with object-oriented or imperative programming, if you look at one of those Ramda pipelines, there's so much implicit, unstated things going on. Like, you'll be totally lost, if you've never seen something like this before. So I get that. So one good way to make and then I had this example too, of some code that I wrote early on in my functional programming career, when to demonstrate that it's really easy to kind of go overboard with pipe and to assemble something that's actually, it's declarative, sure, but I wouldn't call this function readable. There's a lot to unpack here. There's some conditional branching logic. This whole thing could be cleaned up by applying some more higher level abstractions, but I didn't know those abstractions at the time, so this is what I did. Okay, so the first thing we can do to make this better is to use good variable names when we're declaring our functions. If you notice, my variable name for this function is quite long, but it's descriptive. It tells you what it does. This particular function I didn't do point free because it's not strictly a pipe outside from the outside, and I'm doing some stuff down here. So, but the variable name at least kind of describes what it does. Using a type system like TypeScript or Flow can give you a framework for actually declaring a real type for these things. That can serve as good documentation. And then the last thing you could do is potentially break up large anonymous compositions. And so what I mean by this is, like, this is effectively one big anonymous function. I'm using a bunch of other little helper functions, but we can actually break this up by anywhere we see a pipe, we can actually, because everything's point free, we can do this very easily. We can break this up and pull this whole thing out and give it some name. I don't know what exactly it does, because I'd have to read the implementation. But suppose I just do the thing, and then if I defined do the thing up here as that pipe, then I've essentially given this quote unquote anonymous function, I've given it a more descriptive name. This name sucks, but supposing that I actually knew what this thing did, I could write a more descriptive name for it. And then instead of having this huge pipe that's really hard to unpack, just refer to a function that does some, that is captures the essence of a higher level abstraction. So anyway, that's one thing you can do to make these things easier to read. How about debugging? A lot of people say that functional programs in JavaScript are harder to debug. And yeah, I totally think this is a valid criticism too. Look, for example, here. Suppose that we have this little simple pipeline. And then if I look at what I'm doing here, I'm passing it some CSV data. And then when I run it, I see I have a bug. It should be converting my numbers to, it should be converting my list of strings to a list of numbers, but I'm getting nan, so I have some bug. So if I was doing like breakpoint based debugging, I couldn't like drop a breakpoint here, because these aren't declaration steps. These are all it's a function call. Pipe's a variadic function. It takes an infinite number of parameters. So there's no way to put a breakpoint here. So what can I do? How can I, like, there's something going on where like the input of one of my functions here is not what I expected. So I need to figure this out. So what I can do, the technique is using transparent helpers. So here's what I mean by that. I'm going to define a debugging function. I'm going to put it in here temporarily until I have my problem fixed. Suppose I had this log me function. It takes an X, and I'm just going to do a side effect with it. Not pure, so it's worth mentioning, but it's going to help me examine the input of the output of the program. I'm just going to take in an X, log it, and then I'm going to return the X back. So when I say that this is transparent, what I mean is that it takes in a value, but it doesn't change the value. It just does some side effect. And I can take this function and I can insert it between each one of these functions, and then I can find the bug. Let me clear the data. Let me clear the output again, and then let's take a look here. So after running the rprop CSV on the passed in data, I get 1, 2, 3, 4, 5. Okay, so that's a string. Okay, that's good. So now after I run split on the string, I get a list of strings that are numbers that can be number. And here's where I have my issue, is that I'm just running the number constructor on the entire list of numbers. I need to run it on every value. So here I need to use the map, actually, r.map. And my mapping function is the number constructor. Okay, so now I'm getting the output I expect, which is 1, 2, 3, 4, 5. Okay, so that's how you would debug an expression like this without any other special tools. So yeah, I mean, it's a little bit harder to debug. I have to remember to go back and remove these things, but it's it at least gives you something. You're not like totally lost. So, okay. Last thing, I think this one's probably the most valid criticism of them all, is that functional programming, especially in JavaScript, can be regarded as less efficient. And so there's really not a good answer to this, because it's kind of obvious when you think about it. Because in functional programming, with the way we've looked at in JavaScript, you're going to be doing many, many more function allocations and more function calls and deeper stack traces and things like that. And so like those things have, a non-trivial overhead if you do them a lot. And then actually using Ramda to indirect all of our functional programming might make things might make the engine, the interpreter, less able to optimize some things that would be more easily optimized in an imperative fashion. So again, there's not really a good answer to this, but the best thing I can say to this problem is that in most cases, it's not going to matter. Don't prematurely optimize. That's a pretty common tenet for clean code. It turns out that it's much more effective to optimize for developer time in, I don't know, like 80% of the cases than it is to optimize for performance. And then, once you know for sure that performance is an issue, and you know that the functional code is at fault, then that's when you refactor. Don't accept a less flexible paradigm, that causes more boilerplate unless you absolutely have to. So anyway, those are my drawbacks. A few next steps before we finish up. We're getting to run pretty long here, but there's a lot to unpack. Okay, so next steps. Ramda adjunct is where you can go to next after you kind of get your feet wet with Ramda. Ramda adjunct is an extension library. The nice thing about Ramda is that it defines a lot of reusable, composable functions that you can use in your programs. The problem is that it's not like exhaustive. For like where like Lodash or underscore might be more exhaustive. So I mean, for example, Ramda has a is nil function, but it does not have a is not nil function. Because it actually turns out that it's trivial to create your own is not nil function by doing a compose of the not function and the is nil function. Okay, so but what Ramda adjunct does is it actually provides you a lot of those like easy to build functions in a reusable, tested way. So if you have any interest, that would be a good thing to use. FantasyLand is a specification for algebraic data structures in JavaScript. That's a lot to unpack, but basically it's like the formalized specification for an ideal world where we can do every functional programming thing that we want to do in JavaScript. And it's the influence, I think, of the Ramda library and some of the other functional toolkit libraries out there in JavaScript. This is sort of the underpinning fundamentals of it all. Ramda doesn't actually strictly adhere to Fantasyland to be a little bit more approachable, but there are certainly more libraries out there, like Sanctuary, that do adhere more to strictly to the Fantasyland spec. So if you kind of want to go deeper down the rabbit hole, that's would be my next step to recommend. So type systems are a good thing to just improve the overall safety of your functional programs, or really any program in general. So check out TypeScript and Flow if you want to have some mechanisms for actually declaring some type for your functions and your data pipelines. And then if JavaScript itself is not enough for you, or not strict enough for you to do real functional programming in, there are these functional languages that compile to JavaScript that you might take a look at. ReasonMLs from Facebook. There's PureScript and there's Elm. Certainly there's more things out there, but these are sort of the biggest ones on my radar. And then if you decide you don't want to even bother with JavaScript anymore and you want to do other functional stuff, then the world really opens up, because then you can start looking at Haskell or OCaml, or if you're a .NET person, F#, or if you're a JVM person, you could do maybe Scala or Clojure. And if you want to dive back into history or do other stuff, there's Erlang, Scheme, and Lisp available too. Okay, then finally, I have a few resources for you I would recommend. Thinking in Ramda by Ramdy Coleman is a really good resource for basically everything I talked about in this talk in a readable format. Randy Coleman has done it with this series. Professor Frisbee's Mostly Adequate Guide to Functional Programming reads like a user manual. It's not quite as approachable as Randy Coleman's blog post series, but it is more comprehensive, I would say. It dives a little bit deeper into the real world stuff and those good things. And then railway oriented programming is one of those like fundamental sort of those fundamental talks that happened in some time back for functional programming, and ended up being very influential. It's just an approachable talk that talks about how you can do pipelines like we had talked about with pipe and compose, and actually be able to build fault tolerant pipelines and have actual real error handling and things like that in there. So if you have any interest in that, railway oriented programming is where I would direct you. And then finally, if you really want to dive deep into the fundamentals and the underpinnings of this whole thing, Structure and Interpretation of Computer Programs is the classical literature for the textbook actually for functional program, like basically your data structures, algorithms class, all functional programming. I've read a little bit of it. I haven't gotten too deep into it. It's an older book, I would say. It's from like the 80s or the 70s. But it's one of those things that the concepts within are so fundamental, they're not going to change too much, which is really unfortunate for the textbooks companies who need to keep pumping out new versions to make those sick profits. Anyway, with that, that's all I had. I know it's kind of a long talk. Hopefully this recorded version, you can put me on double speed or skip past the boring parts. So anyway, if this was a live talk, I would take this opportunity to take questions. This, of course, is not a live talk, so I don't have the opportunity to take questions. So we're just going to make Google Hangouts freak out here again. And then we'll have a look at my ugly mug again. Maybe. I don't know. Opening up cameraman. There we go. Hey. All right. Okay, so that was a lot. But I hope that this talk, this helps, if you have some interest in functional programming, especially in JavaScript, and you never really known where to get started. I hope this can help you get started with that. I'm always on DevICT Slack. Hit me up if you have any questions. I'll make sure the slides that I had here end up in the video description somehow. And then, other than that, I will see you guys later. Where's the stop?